So that was an interesting challenge to put something together that's interesting enough and fits in 20 minutes. But thanks for the opportunity. See this as a conversation starter, right? I tried not to make a product and vendor presentation. I branded myself, so you know that I'm from a vendor, but I tried to bring an interesting thought to you, so I might make controversial statements. Don't kill me for that, right? Come to me and discuss them with me because I'm happy to defend. And of course, I have to oversimplify stuff, right? So don't take everything literally. But to talk about HPC and AI and how things are different, I think we have to simplify a few things to make a point. My name is Heichler. I have like 20 years of HPC experience now. So I come from the HPC field, but since 2.5 years, I'm working for VAST. And it's a bit of a mission right now to talk to HPC sites and try to bring the AI perspective from the industry to them. Because realistically, most of the AI that happens is not at the core HPC sites. So the biggest AI factories in the world, if I may use that term, exist outside of these core sites that are so good in running large compute infrastructure, but they have not built an AI factory practice. This happens outside mostly. And it doesn't mean that there isn't valuable contributions, as we have seen over the last 1.5 days, from the HPC community to the AI community, right? But the end-to-end life cycle of an AI workload, if you want to call it like that, happens outside of the core HPC sites typically, right? The data comes from somewhere else, and the inference happens somewhere else, and the value is produced somewhere else in many cases. So why VAST is important in that, or why should you listen to us, right? VAST is a relatively young company, 9.5 years old. 6 years we are shipping a product, but we are 1,000 people strong in that time, or we grew 1,000 people strong, and that was largely due to AI. Most of our customers are in some form attached. You're making that face. I'm not sure if I'm doing something wrong. Something in my face? No, okay. So we are coming from the world of AI. We have been born in the world of AI, right? So we can break with a few paradigms, and the market is accepting the offering. And the one thing that I would really want to leave with you is VAST is obsessed with customer experience. So most of our customers are helping us to make a better product. Most of the features we build into the product are induced by customers and by discussions with customers. So we work with customers to build those things, and many of those are AI people, if I may call them like that. So our largest customer base includes like I'm not sure if you're doing things around me then. Okay, so most of our customers are attached to AI in one form or the other, right? So we work with the largest model builders, including XAI and others, building foundational models. We work with what we call neoclouds, the AI CSPs like CoreWeave and Lambda, the big ones, but also the sovereign ones in Europe, like Sisters or Scaleway or Tiger, that have a very strong focus in their home markets. And we drive enterprise AI, and we just released, like I think at GTC, an interesting use case about NHL and how you can use AI to basically leverage the value of the existing videos that you have to create new products. So that is outside of the research part, but it's really into putting it to work. So that's where our AI perspective comes from. But at the same time, a large customer base that we have is HPC sites, core HPC sites. So we run numerical simulations, high energy physics, and so on and so forth on our systems day in and day out. So if you want to talk to some of our customers in that field, I can just encourage you and ask them what their experience with the VAST system is. And of course, I hope it's positive, but for most customers, I can vouch it is positive. One is here at the CSCS as well. So CSCS is a customer, unfortunately not for the core HPC system yet, but we're working on that. Okay, so when we look at HPC and how we construct storage in that, how to build an HPC storage system was a question like 25 years ago, right? Like, how do you build that? You start with the applications, and the agreement is we use POSIX, we use files. That's what everyone wants, so we build a storage system using that. We optimize for large block sequential, right? Because back at the time, it was disk drives, and they like this. So we try to optimize everything we do in the stack for large I/O interaction with the storage system. And then we put scalable read and write performance on the requirement table, and then we put scalable capacity there, and then we end up with the concept of a parallel file system. And that is what has driven HPC for 20, 25 years, and it's accepted concept. The interesting part when you look at the whole industry is that concept never left this room, I would say, right? Like the HPC community. The enterprise market doesn't care about this. There's like a 10x market out there, and nobody uses a parallel file system for their main enterprise workload. There is parallel file systems in enterprise sitting somewhere in the corner, not at the core of the business, but at some development department. And why is that? Well, the deal with the community basically is the community accepts a complexity and a minimal set of features to get as close as possible to the bare metal performance. That was the deal. That you get out of a parallel file system. And also, they accept the complexity of data management. So anything more complex than storing a file, you have to implement in libraries, in data formats like HDF5 or something like that. If you need a database, well, implement something yourself. It's not a service-oriented approach. Parallel file system is brutal performance for file. That's it. And that's good, right? HPC needs that. And if we look at AI, then HPC people often look at this, isn't AI just another HPC workload? And 3 years ago, I was one of those people, and I thought, like, this is just looking like HPC. But it really isn't, because the paradigm is different. HPC often takes a fixed input, calculates on it, and produces a fixed output. And that's what we focus on in HPC, driving this as fast as we can. While AI has these extremely complex data pipelines. We need to get the data somewhere, refine it, put it into action, maybe create a model out of it, maybe infer with the model, take the output, feed it back, retrain the model. So it's a lot more around the data at the core of things. Of course, HPC needs data, right? A high-energy physics workload doesn't work without the data. But the center of attention was typically the compute part. So that's how the difference, or how I would describe the difference. And if we look at how AI, we're doing that on purpose. So if we look at the AI pipeline, I mean, you're looking something like that, right? You start on the left-hand side, you collect some data somewhere, different data sources can be in a lab, can be outside of a lab, can be all around the world, can be distributed. Then you refine the data, you basically squeeze it down into something that you can train off, and then you train a model. And with that model, then you go into fine-tuning of the model, then you infer with the model, then you maybe feed back into your training because you created something that you want to train a different model with, or you train the same model on generated data, which is a discussion right now, right? Does it make it a model dumber or better, right? Can we differentiate between the two? And the only thing that looks like HPC is basically in that red box, right? The GPU-based training, this looks like an HPC workload. But what has to be acknowledged is that 80% of the work happens outside of the red box. And the biggest challenge that we see in our commercial CSP customers that offer basically services in the red box is, how do I get people into the red box? How do I enable them to consume those resources and train something if I'm not offering the services left and right of this? So this is the big challenge that we see, and this is a big challenge also moving HPC sites, becoming AI factories, will be faced by them. You have to get people into the red box. So practically, when we look at HPC and AI, how do we compare, right? I talked about file. On AI side, we talk file, we talk object, we talk databases, like columnar databases, not necessarily transactional databases, but also transactional data warehouses. So we want to ingest data while we compute on it. When we talk about RAG, we talk vector databases, we talk event brokers, because we need to create those pipelines that respond to change data. All these services are important when you build for AI. They don't matter if you build for HPC. HPC, optimizing for sequential, I mean, we can argue on how much that is a reality on a multi-purpose HPC system. I mean, sequential, from a storage perspective, often looks like random because you have multiple jobs running. But on AI, it's inherently random. It's nothing else but random. And you will not be able to optimize this away because it's a part of the concept. I will show in a minute. Yeah, single-tenant resource, HPC, multi-tenant resource in AI. As soon as you have multiple people bringing their proprietary data onto the system, you're having a completely different discussion, especially if you start working with the industry. This is the core of their business, their data, and they will only trust you with that if you have a multi-tenant environment. So we have to build multi-tenancy into it. HPC, 20, 30, 40 years of experience in some departments. AI is rapidly changing, and I just had this discussion in the break somewhere. The biggest challenge in AI is exactly that, the velocity of things changing. People don't optimize stuff because the time you need for optimizing, 3 things have changed on the way. So we are looking at something that's rapidly changing fundamentally, even in how they access data. So we have to keep up from the infrastructure perspective, while on HPC we know the requirements more or less, and we can optimize with a relatively narrow window for it. And yeah, then batch processing versus interactive use. That surprises HPC users often. In HPC, we are used to Slurm and other schedulers, and we fire the job, and we wait 2 days, and we get the result. In AI, typically, there's a huge portion of interactiveness, not that 10,000 GPUs wait for me to press a button, but data scientists experiment on interactive sessions. They have their Jupyter notebooks, and they look at their data, they experiment with it, so they need instances that they can spin up in a second and don't wait for it. And on the other hand, even if you train a huge model on 10,000 GPUs, you will interact with the training. You will look at the output. The MLOps engineers will look at the output. They might stop the training, restart from an earlier checkpoint. They might take portions of the model and test it and to see if it does what they want to do or change parameters while they do it. So there is interactiveness happening, even if the model trains for 3 months. So that's a different paradigm on how you deal with your system. And then I typically have these discussions on why is AI random and why can I not optimize that, right? Like, I mean, if I optimize and I get the random component out of the way, then I can use cheaper storage systems, for example, because I don't need all flash then. But AI is random. The moment you start training something, you cannot train on a sequence of things because now you're training for the sequence instead of for the content of the data that you're delivering. So it's an inherent component of randomness, and you cannot get that away without producing a biased model. We talk about different data sets, small and large, but even if we have large data sets, if you start to do feature extraction, you do small I/O to large data. If you look at all the wheels from cars and you only have videos of cars, the files are large, but the I/Os are small because you're looking at frames that show exactly what you want. So also, from a storage perspective, a random access pattern. And we are mixing workloads all the time. We cannot guarantee a fixed set of workloads that is running in a certain composition, like, I don't know, a weather site could. We will always, or AI systems always run training, inference, maybe even data prep, because they use the GPU resources to do some of that. And that will always mix, and it will change in composition. So there's not a fixed portion you use for one or the other. So all these things, they cannot be taken out of the equation without fundamentally changing it. Maybe in 10 years we have found a way, but right now the world is changing so fast that as a result, all the AI factories that are existing in the industry part, which, you know, the model builders and the AI CSPs, they are all built from all-flash architectures. There's nobody implementing something different because tiering as a fundamental approach is too expensive, it's too costly. You're offloading data management to your users. They don't have time for that. They need to keep up with the rapid development on the, you know, all the AI papers coming out and all the training methods and the frameworks. So that's a decision being taken by the market, more or less. And still in HPC, we have that mindset of optimizing things and implementing tiers and putting the cheapest possible solution for the maximum output to work. And that might set one up for failure in a rapidly changing environment like AI is at the moment. And when we talk about changing fast requirements, we talked about checkpoints yesterday, right? And you compute and you checkpoint, and the checkpointing has to be as fast as possible so you can go back to computing. Makes sense, right? This is how it has been done. But the frameworks or the practitioners move to asynchronous checkpoints now. So the consensus seems to be that global file system checkpointing is still not good enough. We start to checkpoint locally, into memory, into local device, and then maybe every 10th or 20th checkpoint we write to global storage. And if we do that, we have changed now what the storage has to deliver. Before we looked at the peak write performance for a given amount of data or a given amount of time. Now we look at my write performance or my write workload is competing with my training input, because the whole idea of asynchronous is that I can keep on training while I'm trickling out this checkpoint. But now I'm having two competing workloads on my system, and I might choke my GPUs just because of that. I might choke the training because I'm writing the checkpoint in the background. So now I'm talking I need quality of service, because if I don't have that, I'm losing cycles that I actually wanted to win back. And we see these framework changes in other places, like the move to object. as well as that requirements for GPU performance, for example, like 2, 3, 4 years ago, everyone talked about I need X gigabytes per second per GPU. With an established practice that includes asynchronous operations, we see those requirements change. And don't take my word for it. There's tons of sources, right? Look up this stuff. Read into what. Yeah, I know. Read into what others are writing about that. And if I find my mouse, I can speed up a little bit. And as I promised, right, I didn't talk about the product yet. Maybe we can do that in the breaks because it's 5-minute time. But the biggest difference when we talk AI, HPC, I think is the users and the expectation that comes from them. HPC users are used to shell scripts, job scripts, submitting something into a queue, waiting for the output and all of these things. In AI, not so much. Most people come from the cloud. They expect the cloud experience, and we heard it in the talk before, right? There is ways to create that, and I think it's an absolute necessity to create that and respect that the expectation is different. AI focuses on the end-to-end life cycle of the data. You need to move people into the red box. You have to help them get there, otherwise there is nothing to train on. You need automated scalable processes to create those environments because they change all the time. And you need to offer them standard frameworks while at the same time allow them to bring their own frameworks. So you need to give them something that is tested and works. At the same time, you need to give them infrastructure that they can run their containers on or that they can bring their own frameworks. So that's, from a problem perspective, the main differences I see. So of course the question then is, how does VAS help with that, right? Like, why do we talk about these things? Well, the first and most important thing is VAS is an all-flash data platform. And all-flash is important because 9 years ago, flash was existing, but it was way too expensive. So VAS set out to basically address that challenge and said, let's make flash affordable. Let's close the gap in pricing. So we are not set out as the next flash company saying we build a faster storage for you. If you just put enough money on the table, we literally have as a mission to drive the costs down for flash. And break down with the tiers. Because for AI, they don't work. You cannot have a tiered system and do AI on your data. It doesn't make a difference if it's training or inference on data. You cannot optimize that away. And when I say data platform, then I mean basically 3 things. So it starts with the storage. So VAS delivers a storage system. That's why people see us as a storage company. It was the first product we shipped. Think 100 terabytes to hundreds of petabytes, single namespace, gigabyte per second to multiple terabytes per second performance. So all the scalability someone in HPC would need for its HPC workloads. POSIX as well as object. So we do both to the same data. It's no difference to us. So we are completely multi-protocol, and we support all these other nice things like GPU direct-to storage. But we didn't stop there. We did build a transactional and analytical database into the system. So the database scales the same way the storage scales. It's just another service out of the system. You can expose a table and you can hook it up with your Spark, Trino clusters, your external analytics environments. It scales the same way, it performs the same way. It does all the nice things internally as the file and object does. And as a third thing, and that is reaching into processing data, this is the data engine. So if you wanted your storage to act on data that it has, then think of the data engine as a set of triggers and functions. So you ingest an image into your storage and you create 3 different versions of different resolutions automatically. There's no batch job scanning anything. It's like an event pipeline. Or you ingest a video and you kick off an AI model, basically analyzing the video and providing you a transcript or a summary of what is in the picture. So that's what the data engine adds. So you're not just having the storage layer or the data layer and the semantic layer, you also have a runtime layer or an execution layer on top of that. All these things together, they make a data platform, and from that we can build all the services that I talked about. So we can build the file, we can build the object, we can build a database, a vector database as services in the system. And just as a last point, before I run out of time, the cost challenge is of course the biggest challenge. We acknowledge that, right? People have limited budgets, unfortunately. The biggest thing we are doing is data reduction. So we build literally hundreds of petabytes in single namespaces that are a single domain of data reduction. And that's a new concept for the HPC community because none of the scale-out systems does any of that. Maybe there's a bit of client-side file compression, which doesn't help you a lot if the file is pre-compressed. We do dedupe in the backend, we do differential dedupe in the backend, and we do compression in the backend across all of your data. So if it's 100 petabyte, then we dedupe across that. And that leads to the effect that we have for most customers at least 2-to-1 data reduction. If your users suck at data management, like most users, then we get more because they have tons of copy data, and we move into the 3-to-1, sometimes 4-to-1 reduction rates. Simply put, you buy 1 petabyte of storage, you get 2, 3, or 4 petabyte of usable capacity. And I think we are pretty unique with that. Well, and we put all that in an enterprise style consumption model, right? You get a single system, API-driven, fully featured, all the things that you need from snapshots to replication, all these things are built in. And it's not hard to operate because it comes with a single GUI, it comes with a single a button to upgrade it, it comes with a service that is not supposed to go down, delivering more than 5 nines of availability, which also in the HPC world is not what the paradigm was, with maintenance windows and maybe 98% of availability. So we deliver all that from a single platform. Great performance, scalability, all the all the capabilities for AI factories, all the services that we need in a composable form. It drives the cost of flash into something that is hopefully more affordable. So it allows to deploy more of the good stuff. And yeah, the full enterprise feature set, dealing with all the things like compliance and security, multi-tenancy, zero trust environments to build AI environments that are really useful to your users. According to my clock, I'm 1 minute over, but I'm not getting a sign here. So. Yeah, I need to leave room for questions. So. Yeah, I'm good. I have 25 more slides.